Creating the summarizer. Let's first of all change our music because this is worst. Okay.
Я инопланетянин, я инопланетянин твой, я инопланетянин, я с другой земли, тебе такого не найти. Я инопланетянин твой, я инопланетянин, я с другой земли, тебе такого не найти. Я инопланетянин твой, я инопланетянин, я с другой земли, тебе такого не найти. Я инопланетянин твой, я инопланетянин, я с другой земли, тебе такого не найти.
Alright, so again, let's do
мое сокровище, все дневные. Что-то в тебе есть магнитное. Тебя нахожу каждый день алмазы, и твои глаза блестят как стразы. В них я вижу Wacky, фантазия, безобразие, безобразие.
like summarizing type.
Я инопланетянин твой, я инопланетянин, я с другой земли, тебе такого не найти. Я инопланетянин твой, я инопланетянин, я с другой земли, тебе такого не найти.
Почему такая красивая луна? Все зимние тайны навсегда познаем. Мелодия тумана, в нем силуэт твой, птица без крыла. Я лечу домой. She's on the start, she's on the start, she's on the start. Я найду тебя в толпе, победа в любой борьбе. С тобою лечу к мечте, с тобою лечу к мечте. Я инопланетянин твой, я инопланетянин твой, я инопланетянин твой, я инопланетянин твой.
Я инопланетянин твой, я инопланетянин, я с другой земли, тебе такого не найти. Я инопланетянин твой, я инопланетянин, я с другой земли, тебе такого не найти.
Без тебя, родная, я не я. Ты моя мания, ты аномалия. С тобой хочу взлететь на небеса. Я все построю сам по белым парусам. И мне не нужно много слов, ты просто будь со мной и все, я. Ведь без тебя, родная, я не я, родная, я не я, родная, я не я.
All right, let's actually get cranking back on this. We'll just see if this whole stream's working. We'll just. Okay, let's just make sure we can hear this. Are we on chat or game? Yeah, we're on game. I don't know why it's not monitoring. So, alright, if we put it into chat, are we now going to monitor? No, it's not going to monitor at all. Okay. Let's keep watching. Are we now going to monitor? No, it's not going to monitor at all. Okay. Let's keep watching. Are we now going to monitor? No, it's not going to monitor at all. Okay. Let's keep watching. Alright. Settings. Audio. Audio mixer. Oh, now you just have to. Here we go. Okay, so we want to monitor. Here we go. Okay, so we want to. Okay, sorry. Yeah, here we go. Okay, let's get back to actually writing some code. That'd be great. So let's go back to what we're doing here, right? So essentially what we want to do is create a super small LLM that's capable of like looking at large context sizes. And that's like the focus of today's session. So essentially what we have right here is a way to monitor 2048 tokens simultaneously, right? So we're going to attend to 2048 tokens, and we're essentially going to do it in various levels of attention. So this first layer here is going to be 2048 tokens that we're attending to, and that's the max context size that we're ever going to look at, right? And so that's going to output, excuse me, essentially 64 tokens. So we're compressing 2048 tokens into 64 tokens. We're going to do the same thing for 1024, compress it into 64 tokens, and then the actual context window that we're going to attend to fully through the stacked transformer layers is going to be this 256 plus 128, right? And that's going to be like a fairly adequate context window for, you know, like 2-paragraph text generation. That's like kind of what we're aiming at in the area of 100 to 500 million parameters. So again, the way this works is that compress down to 64, compress down to 64, and then keep this at the same size. And so then what we have when we add all those up is 512 tokens that we're actually going to send through the encoder stack. So that's kind of the plan of what we want to build. So let's actually get to implementing this. So where's our code? Okay, here's our code. So essentially what we're going to do is make this class called Summarizer, and that's going to do everything for us. So the important things to note about this, what I'm trying, is that we have an embedding for each summarizer, right? So this first summarizer, so each of these are going to like have their own summarizer. Right, so what the hell? Alright, let's just refresh this. So what we're going to do is have a summarizer class that outputs this. So this is going to be a summarizer class. This is going to be a summarizer. And then this is going to be a summarizer. And so then what we're going to do is like concatenate all the outputs, just like how we have it here. So this is going to contribute 64 tokens. This is going to contribute 64 tokens. And then this is going to contribute 384 tokens. And so we're going to take that 512 tokens and then just pass it through a normal encoder stack. And it's going to attend to all these tokens, but it's going to have compressed basically all of these into 128 tokens, and then these into well, it won't have compressed them at all, but it will pass them through multi-headed detention for one pass. And then we're going to go into like a normal encoder stack from there. So let's start doing that. I already have a lot of the code written already. So here we have our summarizer. We're implementing it here. So we're still in the embed portion. We're writing this function. So we have that embedded sequence, which is now going to be and then this is going to be like your batch size and tokens, and then your embed dimension. And so then that just gets pushed out right here. So now we have our embedded inputs, right? And so now we just want to perform attention on it. And so we're going to use our multi-head attention, where the embed dim. No, I have to save these as class variables. Alright. Multi-head attention on. Oh no, you know what? We already implemented it here, so we just have to actually pass it through. So the attended tokens are going to be attention output, self dot attention of the input sequence. But first, the attention input is going to be let's do summary tokens. And we're going to expand them. This also has to happen here. Okay, so now we're going to make batch size number of summary tokens. We started attention output right here of the attention input. Input sequence, input sequence. So now we have our attention outputs from the input sequence. Okay, so that first is true here. Okay, so we've expanded our attention input, so now we have our attention output from here, and now we have our attention output. So now we have the summarizer class, right? And so now what we're going to do, let's just use this class, and then let me figure out where to put this. Alright, so we're going to have a large summarizer, and then that's going to be 2048, right? Because again, what we're doing is we're taking these 2048 tokens, summarizing them into 64, 1024 tokens, summarizing them into 64, and then taking the 256 by 120 plus 128, and then just summarizing those. So, of course, the embed dimension is going to be self.n embed, whatever that ends up being, num heads equals self.n heads, and n tokens, that's going to depend, because when I made mini transformer Steinshark, we don't really have that as a parameter, so we're just going to have to set that to whatever we want. So for now it's going to be 64. The device is going to be device. This was originally written for multi-GPU, which unfortunately we don't have. So I'm going to have to refactor all this. Alright, so there we have our device, and the device is self.device. Alright, now I'll have a summarizer medium, right? Same concept, except the only difference is that we have 1024 tokens, and then we'll have the summarizer of the actual token size, which is going to be n positions, and then the number of tokens is also going to be n positions. So here we have the summarizers, which are going to give us embedded outputs given a token sequence input. So what we don't need is an encoder block anymore, because these all do the encoding themselves. Alright, so each block returns a sequence of embedded inputs. Alright, so each of these are going to do embedding, multi-headed attention, and summarization. Okay, so now what we're going to do is the follow on, oh my goodness. Follow on transformer stacks. So the transformer stack is going to be, what did we call it? A decoder layer. So it's going to have n embed. We'll just transfer all the class variables and pass them as the variables to instantiate the class. Right, I'll just recap these real quick. N embed is our dimension of the embeddings, right? So I think we have 1024 in our actual trainer. And that's just basically how many numbers encode each token of the text. So that's the embedding. The number of heads is like how many times the embedding is like split into different sections. and each of those come up with their own interpretation of the embedding. NFF is like the size of the feed forward network. So what you do is you have like attention. You have attention, which attends to all the tokens in the set. So it's like each of these tokens look at each of the other tokens. Right, it's like a graph there. And then we have some linear layers. And then NFF is how much bigger that becomes before it comes back down to its normal size. And so that lets the model be a little more expressive. So I think NFF is about double the embedding dimension. And then dropout. I don't think we have that as a... Oh, we do. So let me just make that class variable. Alright. Dropout again is like how much we're gonna ignore every time we do a forward pass, and it randomizes which ones it's choosing to ignore. And that just makes it a little more robust, helps it learn. So we have our transformer stack, and we're going to make self.n layers of them. So we're just going to stack them on top of each other, hence the name. And we'll make it a sequential, so it all just passes forward pretty nice and quick. And then, of course, the LM head, right? The language modeling head. What it's going to do is actually take the final embeddings and then convert that to probabilities of each word, right? So this allows us to actually do token generation. Alright, so now we have summarizers, which is like the first step everything has to go through. This goes from tokens to embeddings. Transformer stack goes from embeddings to embeddings by the end. And then the language modeling head goes from embeddings to probabilities by the end. And then, all right, so we go through basically, actually, this needs to be fixed. We need all of these to be put onto the device. This is a little redundant, I understand, but whatever. Allow for language modeling with 2 L's. And then we'll get the actual number of parameters because we kind of care about that. Okay, we have a generic name for this model, so that way we're, like if we want to change something, we won't overwrite changes. Stats help for training, and then we'll initialize weights with Javier uniform initialization. Alright, so we're going to have to change up this forward pass. So let's just scrap this. Right, so input IDs is going to be a batch size by n tokens, number of tokens. And then target IDs is going to be batch size by 1 token. It's essentially the next token after the whole sequence, right? So it's the next token, but it's actually like shifted by 1. So it's actually the same size, it's just the next token. So if you think about it, like, let's say batch size is 1, and each of these tokens are like 1, 2, 3, 4. Then the target IDs would be 2, 3, 4, 5. So it's like, what's the next one from here? That's going to be the target ID in that same position. So input IDs, we're actually going to have to split this. So context IDs is going to equal, so again, like we're going to pass in where n is 2048. But the actual context is everything up until the last n positions. Because n positions is like what a normal transformer stack would actually attend to. And really, this is actually going to change. So, the large context IDs is actually going to be equal to, it's going to be the input IDs of everything, Input IDs dot copy I guess we do need that. And the source, we'll just use torch.copy. Or it's clone. The input IDs. So we'll clone the input IDs. What is memory format? Yeah, whatever. So large context IDs is going to be the entire input sequence because we're going to pass 2048 tokens in. Medium context IDs is going to be the input IDs, include every batch, but we're only going to include up to the last 1024 tokens. And now for the actual input sequence, it's going to be the input IDs up until the end positions. Alright, so what that did was create these vectors. So now what we have to do is get our token sequence out of the large context IDs. So large context embeddings, and the embeddings, not the token sequence, is going to be the large summarizer let's actually call it on large context IDs, because the summarizer forward only takes the input sequence. Alright, let's let these know what they are. They're summarizers. We'll just make the code cleaner. Here we go. Medium context embeddings is going to be medium summarizer on the medium context IDs, and the sequence embeddings, or the, let's just say input embeddings, is going to be the input sequence on, no, sorry, summarizer actual on the input sequence. So again, this is going to be 64 tokens. I mean, embeddings. This is going to be 64 embeddings, and this is going to be n position embeddings. Actually, you know what? So what's going to have to happen is n positions is going to have to subtract 128 from it. So let's do n positions minus 128, because of course, you know, let's add that as a class variable. So n tokens large to make it 64, n tokens medium is going to be 64, and then n positions is going to be the total sequence length. So we won't explicitly give it the actual sequence size that we take from the actual summarizer. So this, let's make these variables. And tokens large equals n tokens large, and tokens medium, and tokens medium. Okay, and then flip that in. Tokens actual is going to be n positions minus n tokens large minus n tokens medium. And just so I don't mess up order of operations, let's make this explicit. Okay, and now we'll just make this and tokens large and tokens medium and tokens actual. Alright. Alright, and we've made that actually So now what we're going to do is our input for the actual encoder stacks. Sorry, transformer stacks. Let's call it transformer. Is going to be torch.cat. So we're going to concatenate cat takes this large context embeddings, medium context embeddings, and the input embeddings. And this is all going to happen in the first dimension, because what we don't want to happen is it to stack, like triple our batch size. We want it to triple the number of tokens, which is the second dimension. Because remember, these are all going to be batch size, token length, and embedding dimension. So now what we can do is say transformer output is going to be our transformer stack on the transformer input. So we're going to pass that through the transformer output, and then the logits are going to be the LM head input on the transformer output. Okay. And now we just want to return the target IDs. Logits and target IDs. And of course, target IDs is actually target IDs. It's just going to be the target IDs up until n tokens actual. Which means I actually messed this up. That's n tokens actual. Nope. It is self.end positions. I was getting ahead of myself. Okay. So there we go. So we have the logits and the target IDs, and now we have the proper forward sequence for the model. So now what we're going to have to do is implement this here in the training loop. So now instead of input size, we're going to have a context size, and the context actually includes the input size. And we already had that be 256 plus 10 or plus 128. Actually, this is in positions. takes end positions and embed. So we have end positions and embed. Then we have tokens, large tokens, medium, which is 64, 64. And then it should be and layers, which, yes, perfect. And heads, NFF, vocab size, activation function, which we never end up using anywhere, which is very interesting. That should probably go in the decoder layer, and activation function equals whatever. I'll just not make it class variable, I don't care. Oh, also that's not real. Okay. So there we go. Okay, so we've implemented this properly. We'll call this model attempt. And we're not going to try to load the previous model. All of these are going to stay the same. This is actually end positions. Actually, this is going to be context size, because we want it to sample context size, but we'll only try to, predict and base the outcomes on that. Okay. And then num tokens is also context size, because this is actually the variable that changes how we sample. So we're going to be sampling through here. Model. Oh, we're going to also have to change the dataset implementation, because the dataset assumes that we have multiple devices. So let's just make sure we implement that in here. So where are the devices? This is actually just a torch duct device, and it's just a single device. There we go. Okay, so we fixed our data set now. This is also in positions. This is also in positions. This is also in positions. Yeah, we'll count tokens through as in positions, as opposed to the full context size, because we're not really processing all of those tokens. So we'll call it that. Is there anywhere else that has an what was it? Context size. I don't even remember what it's called. Let's just run it and see what happens. Alright, let's train this thing. Train out 5. And in vocab. Where is this? In the summarizer. In vocab. So apparently we don't have a vocab size. We never passed in a vocab size. Alright, so now when we make a summarizer, we'll pass a vocab size. Device. We replaced device with it. So that's actually going to be... where are the vocab size? In vocab. Okay. Replace this whole thing. Replace this whole thing. And it doesn't like that we have a non-keyword variable. And vocab equals n vocab. And vocab equals n vocab. Cannot assign module before the init call. Alright. So we'll call super on the summarizer. There we go. Summarizer takes 1 position, but 3 were given. Alright, where's this happening? Summarizer.init. 1, 2, 3, 4. That's 5 actually. Who's saying that? Am I doing super wrong? There we go. Okay. List is not a module subclass. Oh, it doesn't like how we made a sequential from this list, I think, which happened. Oh, really? Wait. This is not a module subclass. Oh, doesn't it? I think it has to be a dictionary. So let's call it string I to decoder layer for I in range there. Alright, that'll like that. No way. What does sequential take? Modules will be added in the way passed in the constructor. An ordered dict of modules can be passed in. Well, this is an ordered dict. Alright, we'll make an ordered dict out of this then, because ordered dict can take a dictionary. There we go. Okay, it's loading our data. I have all the token, or all the data set pre-tokenized, so it just loads the tokens. I didn't think I had that many. Okay. Each numpy file is... Oh, okay. Yep, the input sequence is just batch size by number of tokens. That's true. I totally messed that one up. Yeah, so... It's not a placeholder. It doesn't even need it. Okay. Alright, we have to load all 400 of them again. Whatever. Waiting. There we go. Alright, let's see what error we get now. Oh, same thing, huh? Where did this happen? In forward of summer. Oh yeah, oh god, we copied and pasted that. Alright, let's just run it one more time. And waiting again. Listen to some good music. This is TLK over here. If you haven't given him a listen, you should. Summarizer has no device. Yep, does not have a device. And we should pass a device. Alright, we'll make a device. Okay, and let's find where we make all the summarizers. Equals, actually self.device in this case. We just need to add this. Alright, this one's gonna work anyway. Loading all the tokens again. We'll keep listening to TLK. Let's see what the error with this one's gonna be. I think it might make it to the training loop where it actually tells us how many parameters it has. Let's see. I think it'll initialize everything. And if it does, as long as our forward method's fine. Oh, and it's not. Oh, you know what this is? This is on multi-head attention. Yeah. This is what happens when you use the torch version of it. You have to explicitly pass the... No, what is this? For a batched query, expected key and value to be 3D, but found 2D and 2D tensors. Wait a minute. Does that mean we didn't embed everything? We got embeddings, embeddings. We embed it. Oh my god. Nope, that's the tiny summarizer. Oh god, yep. We use input sequence instead of inputs embedded. Okay. Alright, we'll go back here. Change this. You know what? This is stupid how we're loading this many. We don't have to load that many. Just for testing purposes. Just sitting here waiting for all that. Load the first 8. Load the first 69. Alright, now let's see what the error is. Double tensor. So it wanted a... Oh, yeah, did we not pass in the right type? So when we're embedding the input sequence expected tensor for argument number 1, which is a weight, to be either a long or an input got a double tensor. Okay, so it looks like the inputs to the embeddings aren't properly casted to longs. Let's just make sure the embedded sequence is a long type. Summarizer. Oh, no. 2. No. Input sequence should be... Okay. And there we go. Okay. It's still a double. I don't know why this is happening. This should be long. Where is this happening? In the embedding position, embedding in the summarizer. The summarizer actual. So somehow it makes it all the way to summarizer actual before we get this error, which is weird because large, medium. Let's make these all. Let's just solve the problem here. Actually, input IDs equals input IDs dot long. Everything should be a long now, right? Input IDs becomes long. We clone. And then summarizer. An input sequence. Alright, now this is happening in a... Nope, same spot. Summarizer actual... Yeah, input embeddings. Only on the actual, which is so weird. No. Let's go into summarizer actual. Nothing's wrong with it. Why is this happening? We cast it as to a long twice. It should already be coming in as a long. But then... Who's actually... Self.embed. So inside of embed, it's not doing it properly. Position embedding is here. Position... Input position index. But why would this be happening for only the actual summarizer? It doesn't make any sense. We'll try this again. Size did not match the size. Semantic embedding plus position embedding. In the actual... Why? Okay, why is it... Why is it running the actual summarizer first? That doesn't make any sense. Because it goes large, then medium, then actual. Alright, semantic embedding plus position embedding. Well, this should be the same size. Let's go back up to the summarizer. So go over the token length for all the batch sizes. Yep, that should be properly. That should be the right size. Input sequence. Size of any tensor alpha 2048. Much past the size of Bravo. So, okay, so Bravo is 0. So position embedding is 0 somehow. The position embedding is shape. Why is there no shape on it? Embedding is position. It's also an embedding that outputs embed dimension, so that doesn't make any sense. Here we go. Position embedding is batch size 2048 by 1024. 1024 by... Oh! Oh, I know why. Okay, check this out. No, end positions 512. And then that gets passed in... Yep. So this gets passed end positions. So end positions is end positions. And then, yep, we pass 64 and 64. So that should mean that there is 384 left over. Where's our end? So it takes end positions and it outputs tokens actual. Huh, that's so weird. Wait a minute, what do we got? Tokens. Tokens actual. Self.n tokens actual. How many tokens actual do we have? Yeah, 384. That's right. Wait a minute, why is Summarizer Actual trying to add 2048 to positional embeddings? So position embedding is shape that, position embedding, shape that, and then... Oh, because it's getting past input. Wait, it's getting past input sequence. Input sequence. Why is it getting past 2048 tokens? We pass it input sequence. Oh, it's through the last, up through the last of them. Cause this, okay, oh my god. Okay, here's what happened. Okay. It's actually the last 1024 token, so just in case this was over. Okay. And trig embed is still being treated as if it's relevant. It will always be trig embedding, so it will always be learned embedding. Okay, remove all mentions of trigonometry. go. There we go. Okay. Again, same error. Input sequence is 32 by 2048. Input sequence is 32 by 2024. Input sequence is 0 by 2048. That doesn't make any sense. Why? Oh. And I didn't put a comma. That would do it. Okay, let's go back. See what's happening. Expected tensor is element 0, but got a tuple. I think that's how cat works. Unless you just pass in all the tensors. Wait, expected tensor. No, it shouldn't expect a tensor. It should expect a tuple. It just told me it did. Tensors. That's very silly. Yep, because we're concatenating all of these tensors together. Expected tensor is element 0. Cast the given sequence. Tensors in the given dimension. All tensors have the same shape or be in one empty tensor. They all do have. They all do have the same shape. And then. Alright. Here's X. And then you just. That's exactly how I have the function set up. Oh, what? So it's saying that this isn't returning a tensor. Summarizer large, summarizer. The embedding sequence is a tensor. Nope. Attention output. Alright, let's see what that is. So attention returns what? Or multi-head attention returns... where's the forward? The forward, a tensor, and an optional... Oh, so we just need that. Alright, that was the problem. Let me check on something. And it looks like we passed it the wrong... I think we passed it the wrong vocab size. Because usually you get that when you pass it the wrong vocab size. Vocab size 120001. And the vocab size being passed here. We're passing in vocab actually into... We are passing the vocab size. Alright, so let's just make sure. Max of input is... Let's see. And max of in... Oh. That might be the wrong place. Max of input is 12,000. Yep, that's exactly what we'd expect. So it can't concatenate these. Let me just make sure we have the right shape here. Actually, it's this way. No, it's happening in forward. Catting the large context embeddings dot shape. The medium and the input embeddings. Alright, let's just make sure this is the actual shape we want. Nope, and we still have the same error, but let's see if it actually... So we're concatenating 32, 64, 1024, 32, 64, 1024, 32, 384, 1024. Yep. So along the concatenation dimension, everything is going properly. So that should be able to concatenate. Source index, source select dimension size. Usually this happens when I don't think this is what's actually producing. This actually might be incorrect. And let's just make sure the cat is actually being good. Nope. Okay, so cat isn't being good. Let's look at the D type. Should have a D type. Make sure they're the same. I mean, that's not what it's telling us. It's saying that we can't concatenate them. They're all float 32s. That's what we want. Concatenates in a given dimensional tangents must have. Why is it not concatenating? Input, medium, large. On dimension 1. We just need the inner dimension to not be the same. And we have this. So that's exactly right. There's no reason this shouldn't be working. This is on many transform. Yep. We have summarizer, 1024, 2048, 1024, and then normal positions. What in the world? Position embedding is 1664. That's just weird. I didn't actually bump one of these, did I? No. 1664 again. Target IDs is all the batches. And that. Somehow I missed that. View says it's not compatible with input tensor size and stride. Alright, I think what's happening is we're trying to compare... what we're trying to compare is... Where does it say... Where is this even happening, actually? Targets equals... Oh, yeah. Let's just check... Logit shape is... It's saying we can't project into batch size by end positions. Let's just make sure our math isn't wrong, because end positions is 512, and we should have 512 logits. Alright, logit shape is, yep, so 32, 512, and then... Wait a minute. Yeah, that's absolutely right. And then it's saying that it's the targets aren't able to be seen as batch size times in positions, which is weird because it should be. Or is it trying to do this? Target IDs. Because really there's only one position per ID. So target IDs, what is target IDs? That should be right. Target ID shape is... So this should be 512. And then this should be 500. Oh. Yeah, yeah. Target ID shape is 32 by 512, yes. And nothing should happen to the target IDs between here and there. And it's just going to be batch size and positions. Let's make sure those are the same thing.